All right, everyone, section 5.5, last section in chapter 5, last section before our midterm too, actually. Very similar to the other ones. We're just going to wind up with a new test statistic, basically. This time what we're going to do is we're going to take two different populations. We're going to grab something from one population, something from the other population, either add them or subtract them. And then we're going to keep doing that, and we're going to look at what that distribution looks like. So if we were in a regular class, I'm not going to do this right now since you're at home alone watching this, what I would have you do is just roll two dice, because it's the basic idea. Is your first population, our number is 1, 2, 3, 4, 5, 6. Your second population is 1, 2, 3, 4, 5, 6. And then we would do a little simulation, see what the mean is, see what the standard deviation is, and that sort of thing. We're not going to do that right now, but that's kind of the basic idea of what we're doing is two different populations and grabbing one person from each one and then going from there. So just a little notation we're going to need in this chapter. I mentioned we're going to actually use the standard deviation squared in this problem, which is called the variance. I think we mentioned this in this class. I'm not really sure. It's called the variance. All right. And we'll see why we're going to need that in just a second. Okay. So what I'm going to do is just show you the properties just like we've done on the other ones. It's the same basic idea. So what we have is we have two populations. All right. So I can show you this all at once. Actually, let's not show it to you all at once. I know that can be a little bit overwhelming, I think. So let's just do this. So we're going to take values from each population randomly and independently. So there's two populations. And the first population has, sorry about that. The first population, so we'll call it population 1, has mean 1. The second population we're just going to call mean 2. And then this one they each have a standard deviation also. It's going to turn out we can't do anything with the standard deviations together, but we can do something with the variances together. And again, if we were in class, I'd probably walk you through all that. We'd probably do it. We're going to see that the standard deviations don't have a relationship, but the variances turn out to do. So here are the relationships. Pretty straightforward. If I get a new distribution where I'm adding them together, what we would expect that average to be are the sum of the two averages. So if I just did this over and over and over and over and over and over, like if we each did it 40 times, the average, remember the average of one die is 3.5. 1, 2, 3, 4, 5, 6, add them together, divided by 6, 3.5 for each one. We also know that the average of the two rows would be 7, right? But if we were to do this, we would, on average, get 7. We wouldn't get 7 all the time. We'd get 1s and, not 1s, we would get 2s and 12s and 6s and 5s and 9s and 12s, but average would be 7 if we were adding them. And then it turns out that the variance, not the standard deviation, however, but the variance of the combination is going to be whatever those two variances are added together. So then typically, because we can't use variance in our formulas, so we're going to use standard deviation. So our standard deviation would be the square root of the first variance plus the second variance. So we add the variances together, we get the new variance, then we take the square root of that new variance to get its standard deviation. Okay. So this would be standard deviation of the sum. We can do the same thing for differences. It turns out that the mean difference, so that should have a minus sign in it. The mean difference is mean 1 minus mean 2. It'd be 0 for the dice, by the way. And then the last one, which might confuse you, the standard deviation is actually going to be the same as it is for the sum. We can't subtract standard deviations. That would make no sense because remember, these are going to have the same standard deviation. The two dice are the same populations, which won't always be the case, by the way, but the two dice are the same population. So that means they're going to have the same variance. And if we do a subtraction, we subtract those variances, we get 0. It means there's no spread at all, which doesn't make any sense, I hope. So the standard deviation of the difference is the same standard deviation as it is for the sum. It's actually the variance first, add them together, but then the standard deviation of the difference would be the same thing, right? So that's pretty much all there is to it. We'll just put a little problem together. Just one example today. It should be quicker because it hopefully feels the same as it is before. So here's the question. We have this work for this company that we make bottle caps and bottles. The bottle caps are manufactured so that they're inside diameter. So this would be like population 1. are the caps. It's going to be roughly normal with a mean of 36 and a standard deviation of 1.2. Oh, I lost some information here. Sorry about this. Those are the caps. Population 2 are going to be the bottles. So I got to look this up. Sorry about this. I was not prepared. Give me 1 second. If I knew how to pause the video, I would. I tried that once and I had to start over, and then I didn't look again. So just real quick, give me 1 second to find this bottle cap problem. You can follow this example in the book also. I think I got it from the book. I hope I got it from the book. If not, I'm going to have to start over. Here we go. The bottles are roughly normal with a mean of 35 and a standard deviation of 1.2. Oh, wait, this was supposed to be 36 and 1. I don't want to change the numbers in case you're going to the book. So this is 1. And then the question is, if we take one of these at random, one cap, one bottle, what's the probability the cap will fit on the bottle? And there's a little bit more to it than that, of course, because we don't want it to just fit on it. We want it to actually be able to tighten. We're just going to ignore that right now. So basically, I'm going to rephrase this question to be more math friendly and just say, what's the probability that the cap is greater than the bottle? Or if we think math, because we're going to have to subtract here, right? Cap minus bottle greater than 0. Okay, that's in essence what I'm looking for. So we're going to get a new distribution now. Everything in all of these problems, everything we do boils down to a new distribution. Find the mean, find the standard deviation, and then normal CDF or inverse norm or whatever they're asking. It's pretty straightforward. So this new population is going to be what we're going to call cap minus bottle, right? Cap minus bottle. So notice the caps had a 36. The bottles were 35. 36 minus 35 or something. By the way, you could subtract the other way, no problem, get a -1 there. Just got to make sure you're answering the question properly, right? So mean is 1. The standard deviation, remember, is we add the variances together, take the square root. So we're going to go 1 squared plus 1.2 squared. That's the standard deviation. We want cap minus bottle to be greater than 0 is all we want. There's my 0, so we're looking for that area. Notice every single problem boils down to find the right mean, find the right standard deviation, and then everything else after that is the same. If you subtract it the other way, you'd have a -1, just so you can see this. You'd have a -1, but then you'd be less than 0. So notice it's going to be symmetrical, so the same area. So all I got to do is the same thing I've done before, normal CDF. From 0 to infinity with a mean of 1 and a standard deviation of 1 squared plus 1.2 squared. So here we go, normal CDF, 0 to infinity, the mean of 1, square root of 1 plus 1.2 squared. Now we get 73.9% roughly. So it's either subtracting or it's adding. The variance won't change. The mean will. Find the right mean, find the right standard deviation, and go from there.